All right, happy Thursday to everyone. Trying to think if there's any announcements. I don't think there's anything to announce really. Homework due next week, of course. We're done with, I guess it's worth mentioning that as of today, we'll be done with the content for the first exam. So the first exam will be 2 weeks from this week. That's the main things worth mentioning anyway. Beyond that, it's also worth sharing that the content for next week, sections 8 and 9, don't have any associated homework. There'll be a nice break for you as you prepare for the first exam in terms of homework anyway. So hopefully that will be a nice break. What's the date today? 10th, so the week of the 21st. So it's, of course, recording nicely. Everyone online can see what's going on the page. We're just waiting for the projector to warm up, so everyone in class can see what's going on as well. What I've got opened up is the end of section 7 on circles and spheres. So for this section, at the end of the section, is just there's 2 more proofs here actually. One of them is just, well, I don't know, they're both kind of interesting. They're both very different. Both of these proofs are proofs that I've not written them myself. I don't think that either one of them is how I would prefer to write these proofs, but that might be exactly why they're worth sharing. So I also thought that they might require a little bit more discussion than what would be put on a video online. And apparently the projector was warmed up. I just didn't have the right input selected. Sweet. I hit the right input. It just, when I look back, it didn't have the right one selected. I don't know what happened. All right, so we want to take a look at the formula for the volume of a sphere. And we're going to do that by considering the volumes of 3 objects. The volume of a hemisphere, which is half of the volume that we're interested in. We also want to look at the volume of a right circular cylinder. And we also want to look at the height of a cone, or we want to look at the volume of a cone with radius r and height r. So in the first spot we have, oh, that's a terrible looking base. So we have a hemisphere, and then we have a cylinder. And we have a cone. So the radius of the cone is r, the height of everything is r, the radius of the cylinder is r, and of course radius is r. Radius is r. All right. want to change how I have my screen input a moment, because I want to look at what I have written up. So you guys can see that now. And I want to see what I have. All right, excellent. So the height is given here by the dashed line. So if we were to consider the slice, the area of a slice of each of these, we wanted to look at the area of a slice at height h of the hemisphere, right? We'd be looking at the slice that's right here at that height. Of course, this is the radius as well. Here's the height. This value here, come on now. This value here, if we were to call that x, right, x is square root of r squared minus h squared. And the area of that disk, that slice, would be pi times x squared. Okay. So the area of the slice would be pi, right, area is equal to pi x squared, but x is r squared, a square root of r squared minus h squared. So this is square root of r squared. Try that again. Square root of r squared minus h squared. Excellent. Squared. And that, of course, is simplified to just pi times r squared minus h squared. Now change the color here a second to, oh, let's go with this green. If we were to find the area of one of these slices, right, it would just be, they're all the same size slice, so it would just be the area of the disk is pi r squared. Okay, that's easy enough. Pi r squared. And then if we wanted to find the surface area of one of these disks, right, since this is radius r and height r, we have a nice linear relationship here. So the radius, when we have particular height, the radius of that slice matches the height that we're at. So this is just pi h squared. And if we pay close attention, we would notice that the area of this disk in the hemisphere is equal to the area of the circle line, or area of a slice of a cylinder, minus the area of the slice of a cone. So if we take that, right, this would be dA essentially, or dV rather, and so we just need to integrate from 0 to h of this quantity, right, times dx or dh. No, it doesn't matter. Anyway, whatever variable you want to call it, doesn't matter. We're integrating over height, so call it h. So we would take these surface areas multiplied by dh to get our volume, and that would give us our change in volume, and so we could integrate. So integrating over h, from 0 to r would essentially give us the volume of the hemisphere is equal to the volume of the cylinder minus the volume of the cone. So with this understanding, we're not actually doing any calculus, we're just recognizing that calculus would give us that the volume of the hemisphere is equal to the volume of the cylinder minus the volume of the cone. And that, of course, is pi r cubed minus 1/3 pi r cubed, giving us 2/3 pi r cubed. But that's only the hemisphere, it's not the whole sphere. So we would have that the volume of the sphere is equal to twice that, or 4/3 pi r. So that's a nice way that we can find, right? That's how we can justify. That's how we know that this is the formula for the volume of the sphere. So I was thinking about it the other day, and what's a half a circle called? Semicircle. So why is half a sphere not a semisphere? I don't know. I just random thoughts. Okay. The surface area of a sphere. This one, this is actually something closer to what I would like. We actually do calculus here, right? We perform an integral. It's so exciting. I like it a lot. But at the same time, there's a few details that are technically not right. And but again, this is what has been presented to me, and I would like to share with you, so we can discuss these slight discrepancies and how they may or may not matter. So for finding the surface area of a sphere, we can use good old calculus. And if we think of a semicircle, and then if we were to rotate this around, then we could get our volume. And so my recommendation would be to use the disk method. That's what I would do, right, for a circle centered at 0 radius. Cool. But slightly different. So again, it's the same process, but we're going to take a band of it. All right, so there's a band, and we want to find that on here to make some calculations for the surface area of just the band, and then integrate over that. And how we'll do that is by actually considering angles instead of x. So we'll look at, let's see here, say we look at this angle given as theta, of course, then this height, let's use this green. This height would be given as r times the sine of theta. And in order to help us observe a band here, if we were to want to integrate over theta, we could get this small angle measure and call it d theta. So we're integrating from 0 to pi here. And if we go over this, then to get the width of this band, we would just take this little bit of arc length. So we can take this little bit of arc length to give us the width of the band, right? R sine theta gives us the radius here, and S, the change, or ds, the change in distance here, would be r d theta. whatever this angle measure is, d theta, the length of this piece is the radius times the angle measure, d theta. And that is the change in distance along this semicircle. So with this idea, we can find the circumference of the band. And of course, the circumference would just be 2 pi times the radius of the band, and the radius of the band depends on what angle we're at. And that distance, that radius of the band would be r times sine theta. So 2 pi times the radius of the band, which is r sine theta. And then the width of the band would be equal to, let's see here, r d theta. So that would give us dA. The change in area is just the change of each, is the size of each band, which would be the width of the band times the circumference of the band. So we have 2 pi r sine theta times r d theta. And then, of course, we would simply integrate that. So the surface area of the sphere would be given as the integral from 0 to pi of, we can combine the r's for r to have r squared, so 2 pi r squared sine theta d theta. Now the goal is to write all of the work for this down below, but for some reason, I don't know why, it's harder to write on this screen. And I don't know why. I noticed that last time I lectured. So I don't have as much room here because for some reason I'm drawing way bigger. And we would find, if we were to evaluate this integral, I have great confidence we can all evaluate this because the integral of sine is, yes, negative cosine, excellent, right? 2 pi r squared are all just constants, so they go out front. So then you're just doing a definite integral of sine theta, which is negative cosine theta evaluated from at 0 and pi. Okay, so you do that and you get 4 pi r squared. Awesome, and that's it. That's the proof. Now, if you want to complain or give concern, this was my concern. I said that the change in area is the surface area of that band, but the surface area of a cylinder, right? The exterior is just the height times the circumference, which is what we've done here. But this isn't explicitly an actual band because it's curved. So because of that, this isn't actually the surface area. I also think it doesn't matter, but explaining why it doesn't matter is not what I can do at this time. I haven't put the thought into it. Hopefully someday I'll be able to share that with whoever might be watching this video in the future, or you guys if you happen to still be here. Maybe I'll figure it out soon. I don't know. I just don't know that I want to put the effort in right now either. But it still works. It still works. If you wanted to find the equation of the semicircle or the upper half circle for on the plane with radius r, you could use the usual techniques of the disk method, and this is exactly what you would find. There's certainly no issue there. So this is just a different presentation of it. That's all that I wanted to talk about for those. So yeah, if you have any questions about that or anything else from section 7. Now would certainly be a great time to ask it, but yeah, just let me know. Thank you for joining us, those that decide to watch this online. Great discussion today. Not a lot about math, so you guys missed out, but we'll see you soon. Have a good one.